Hi everyone, Group 7's presentation is on urban safety monitoring.
Urban safety monitoring uses technologies to detect real-time hazards like earthquakes, radiation, and shooters. This presentation reviews papers on community-based sensors for earthquake detection, soldier wearable networks for shooter localization, and radiation localization in urban environments. We'll also cover numerical simulations for urban road collapse and the role of information sharing in radiation sensor networks. These technologies enable faster emergency responses, improve public safety, and enhance urban planning. This paper addresses the challenge of detecting and locating shooters in urban areas where traditional systems struggle due to acoustic and noise. Quick detection is crucial, as gun violence is a serious threat. The system uses soldier wearable sensors to capture acoustic signals from gunfire and employ algorithms to localize shooters and classify weapons, improving response time and saving lives. Field trials were conducted in military facilities to test the system's ability to detect shooters under urban conditions. The system showed high localization accuracy and could handle multiple simultaneous shots. However, its reliance on acoustic signal can be disrupted by environmental noise, reducing its effectiveness in certain scenarios. Future research could integrate visual or thermal sensors to improve robustness. The second paper focuses on urban road collapse, a major safety concern. The study uses finite element modeling to simulate how underground voids affect road structures. The findings highlight how cavity size and depth influence collapse risk, providing valuable insights into road safety and infrastructure planning. Simulations showed that larger cavities beneath the road led to higher collapse risk. However, the study focuses on no-load scenarios, not accounting for real-world factors like traffic. Future research could incorporate real-world load simulations, considering factors like traffic and construction to better understand collapse risk in urban areas.
Today I'll be sharing some insights on the earthquake sensing systems. It talks about how we can use the community-based sensors like smartphones and IoT to detect earthquakes. For example, like your phone can be like a mini sensor to provide crucial data quickly and cost effectively. It talks about the alarm system, which is a real-time earthquake early warning system that's being used in California. For example, like you're in LA, you can get a few seconds warning to take cover before an earthquake hits. Now, both papers have been shown to enhance real-time detection and alerts for earthquakes, rapidly and accurately giving the community and responders crucial time to prepare. Now, this can help in reducing injuries and saving many lives. It can be challenging to detect earthquake using community-based sensors. This is because some areas may be lacking in the network system. Now, this issue can be fixed by leveraging your smartphones for scalable detection. Now, for the paper 2, it focuses on the need for rapid real-time earthquake detection in California, because the timely alerts can be very crucial in reducing casualties and damages. Now, the author uses the community-owned devices and advanced algorithms for these centralized detection. Because, for example, like the Tohoku earthquake in Japan, similar systems can be provided to give early warnings that can save many lives. So the final result for the first paper, it shows how we can use the high detection accuracy for earthquakes of magnitude of 5 and above with a low false positive rate. However, this relies heavily on the simulation of data, which may not be very accurate or fully captures the real-world scenarios.
So the same issue can be said for paper 2, which is the rapid hazard assessment and early warnings signaled by the alarm system. But again, because it uses the simulation of data, it's not very accurate. Thank you.
I'll be presenting about methods to detect radiation sources. The compulsory paper is about identifying low-level radiation sources using sensor networks. Radiation bombs used for evil purposes such as terrorism can be known before they are set off, as they affect a large area and cause severe health problems to people. The challenge is that radiation from the background is low, and most bombs are stored carefully, which makes the radiation emitted by the bombs also low. This makes it hard to detect the radiation sources. Moreover, there is randomness in the radiation signal since they are Poisson distributed. Geometric difference triangulation is used to identify the location and strength of unmoving radiation sources using sensors. All sensor readings are put to SPRT to decide if a radiation source is present or not, or if more readings are needed to decide. Experiments include simulations for low radiation sources and lab test beds for high radiation sources. This paper achieves the user-specified levels of false alarm and missed detection probabilities while ensuring a small number of measurements are needed to reach a decision. Some limitations of this paper are that SPRT can only detect unmoving radiation sources. More time is also needed to collect measurements when SPRT cannot decide if radiation sources are there or not. These limitations can be addressed in the second paper about detecting low radiation moving sources. Although sensors must be close to the sources to detect radiation signals, we cannot have many sensors in a network due to cost issues. The challenge of moving targets is that sensors have less time to decide if the moving target carries radiation sources or not. Each sensor uses Chernoff bound to see if radiation sources are in the moving target. The quality and quantity of information affect the decisions made. Various simulations of single and multi-hopping transmissions were tested to understand how performance and cost change when the time given to make decision and sensor communication topology changes. Under various movement trajectories of the source-carrying target and sensor topologies, the paper achieves good performance.
Hi everyone, I'm Qi. The first paper aimed to detect multiple sources of radiation with the aim of identifying RDDs or dirty bombs. This was motivated by the lack of existing techniques to identify multiple radiation sources in today's world. Current existing techniques were only able to identify a single source and could not be extrapolated to multiple sources efficiently. The second paper aimed at accurately identifying a single radiation source from environments with high noise, and this technique will be built upon and utilized in paper 1. Both of these papers are important as early detection of potential dirty bombs can help to save lives. The second paper proposed a new ITP algorithm which helped to improve model performance, and the first paper built upon this ITP idea and implemented its own ITP fusion algorithm. This novel algorithm proposed in the first paper is able to handle multiple radiation sources without prior knowledge of the number of sources. This makes it feasible to be deployed. The experiments were carried out via simulations in which the authors mimic the complex urban environment settings. The authors use accuracy, false positive rates, and false negative rate to assess the model's performance. The model achieved high localization performance and can handle multiple radiation sources, even in background with increasing radiation levels. The algorithm performance was further improved in the presence of obstacles. The authors acknowledge that the algorithm performance will be impacted in the case of weak radiation source, and the model will also be impacted when there are more radiation sources. Thank you.
This is our team members' contributions. Thank you.